This is Geometry Unit 6, Lesson 3 on proving triangles congruent using angle, side, angle. So, yesterday we talked about side, angle, side, where you have to have two sides and the included angle congruent in order for the triangles to be congruent, and we proved it. Now, the second way to prove triangles are congruent is called angle, side, angle. And the name angle, side, angle, or ASA, is if two angles and the included side of one triangle are all congruent to the corresponding angles and sides of a second triangle, then the two triangles are congruent. So this time, because it's ASA, we need two angles and the included side. And remember, the included side means the side between the two angles. So that's what that means. So, again, we're going to prove that those points really do line up. If we're given that triangle ABC and A prime, B prime, C prime are here, and we want to prove that they're congruent using angle, side, angle. Let's assume that angle A is congruent to angle A prime. This angle is congruent to this angle. Angle B is congruent to angle B prime. Here's B prime. And side AB, which is the side between the two angles, is congruent to side AB prime. So this side is congruent to this side. So we have angle, side, angle, angle, side, angle. So those corresponding parts are congruent. We want to prove that they are actually congruent. So we want to prove, using rigid motions, the triangles are congruent. We want to prove that A prime lines up with A, B prime lines up with B, and C prime lines up with C. So let's see what we can do. So let's take our triangle here, and the first thing we're going to do, just like we did on the previous one, is we're going to translate along A prime to A. So here's A prime, we're going to translate along to here, like so. So this goes like that. And you end up at the triangle here, where A prime ends up at A, so that proves that A prime and A are the same, will correspond. Then B prime will end up at B double prime right here, and C prime will end up at C double prime here. So now we already know right here that A prime corresponds to A. So there's my first point I know lines up. Now I'm going to take this dotted triangle, I just move here to here, and I'm going to rotate clockwise around A. So A is going to be my point here that I'm rotating around until AB prime, the ray, right here, B double prime, excuse me, I'm going to rotate that until that coincides with the ray AB, so that'll end up right here. So if I do that, and AB we know is congruent to AB prime, because we said that up here, here's AB and AB prime, it's still congruent because of the rotation and a translation, the distance is preserved. AB and AB prime is the same, so that means that B is congruent to B prime, double prime. Okay, so this is going to line up here. This point becomes this point, and they line up perfectly because the distance from A to here is the same as the distance from A to here, because distance is preserved. Now, if I reflect this triangle over AB, this triangle right here, and I reflect it over AB, remember that we know that these two angles, BAC, which is this angle here, and BAC prime will correspond. So if I fold this over. So, and that means that this ray, AC, will correspond with this ray, AC triple prime. So when you fold this over, this lines up over here. Now, we know that ABC is congruent to ABC because we were given that. A triple prime, yeah, okay. So this will correspond with this. So there we go. That means that this ray and the other ray will will cosign with ABC. So that means that C triple prime will line up with C. So because of the way the angle measures are, angle measures is preserved. When I fold this over on here, this angle and this angle will be congruent. And because this angle originally it was the same angle, we know that that angle will be congruent. So that means A corresponds to A, B corresponds to B, and C corresponds to C, and all of those points coincide, so that means the triangles line up perfectly. So what we have just proved, if you have two angles of a triangle congruent, and the side between them is congruent, we can automatically say that the triangles are congruent. So from what we just proved, the image of A prime, B prime, C prime is ABC, so that makes the two triangles congruent. Now, how does this apply to actually proving a triangle is congruent? We now know why it works. Let's actually use it. Let's apply the angle-side-angle postulate to prove congruence. So say we have these two triangles and I wanted to prove them congruent using angle, side, angle. Well, first of all, I need one corresponding pair of angles congruent. Now say I knew what angle A was, all right, and I knew what angle D was and they were the same. So angle A would be congruent to angle D. All right, now the side depends on what other angle we have. So let's say that we had angle C was congruent to angle F, and we proved somehow that angle C and angle F were congruent. It would be right there. So what side would we have to prove congruent in order for ASA to work, angle, side, angle? Well, what side is between those two angles? Well, it would be AC and DF, because the endpoints of the segment are the angles that we got. So this is angle, side, angle, angle, side, angle. So if AC is congruent to DF, these two triangles are congruent. Triangle ABC is congruent to triangle DEF by angle, side, angle. So notice here, they correspond. A corresponds to D, B corresponds to E, C corresponds to F. Correspondence matters. Be very careful of that. So we have proved angle, side, angle. Now that we've proved that ABC and DEF are congruent, if we know now these triangles are congruent, can we automatically say that this side BC and this side EF are congruent? Yes, we can. Because this is a theorem that we have. It's called corresponding parts of congruent triangles are congruent. It's abbreviated CPCTC. CPCTC says if two triangles are proved congruent, any parts that correspond, whether they're sides or angles, that were not used in the proof method are also congruent. So even though we used angle A, angle C, angle D, angle F, and this side AC and DF, we can say BC is congruent to EF. We can also say angle B is congruent to angle E. This angle and this angle are congruent. And we can also say that side AB is congruent to DE. So this is a very powerful theorem. It works because the definition of congruent says if two triangles are congruent, then all the corresponding parts are congruent. Well, we just proved the two triangles are congruent, so all the corresponding parts are congruent. So what this means, and also because the rigid motion preserves distance and angle measure, everything's going to be the same if the triangles are congruent. It doesn't change. So CPCTC can be used if you prove the triangles are congruent. And it doesn't matter if it's by side angle side or angle side angle or any other method that we're going to learn. Once you've proved the triangle's congruent, you can say any corresponding part of the triangle is still congruent. All right, so let's try a proof using angle, side, angle, and CPCTC. We are given that AC bisects BD at E, AB is perpendicular to BD, and CD is perpendicular to BD, and we want to prove that triangle ABE is congruent to triangle CDE, and that angle A is congruent to angle C. So I wrote out my little plan here. I know this is going to be by angle, side, angle, because this is the lessons on angle, side, angle. I want to prove the triangles are congruent using angle, side, angle. So what I'm going to do first of all, for my own reference, I'm going to draw these two triangles exactly the same way, so they correspond. I'll put it on solid so I can draw them. All right, so I'm going to draw, here is triangle ABE, and then I'm going to draw triangle CDE exactly the same way because we want the points to correspond. So ABE, CDE. Here's my two triangles. All right, now labeling them so they kind of look like what we have, A, B, E. So A would be up here, B, E, and I want to label them exactly the same. A is to C, B is to D, and then E is to E. So there's the two triangles. So this helps me so I make sure I've got the right ones corresponding. All right, so let's do our little plan. All right, AC bisects BD at E. All right, so here's BD, and AC bisects it. So what happens when you bisect a segment? You get two congruent segments, and that's not the side of the triangle. So if E is your segment where it's bisected, BD is bisected, what two segments would be congruent? Well, BE would be congruent to BD. Isn't that a side? Yeah, that's a pair of sides. Let's see, BE is congruent to ED. There's a pair of sides. So I can prove side using bisector. All right, so let's write that down. You don't have to do them angle, side, angle in order. This is just to help you organize a little bit. So, AC bisects BD at E. So that's given. Now, from the definition of a bisector, BE is congruent to DE because a bisector divides a segment into two congruent segments. So I have the side part of this. This is the side. All right, so that given is done. I've used that one. All right, then I have these two givens with perpendicular items. They probably have the same reason. So let's look what we have. AB is perpendicular to BD, and CD is perpendicular to BD. Well, what do perpendicular lines make? Well, don't they make right angles? All right, so AB and BE, that would be a right angle there. And CD and DE, that would be a right angle there. So, what do perpendicular lines make right angles, and what do we know about right angles? They're congruent. So I can get a pair of angles by getting right angles here and here. So here's my next step. My given is AB is perpendicular to BD, and since it's the same reason, I'm going to put it on the same line. CD is perpendicular to BD, that's given. And then what I ended up with was congruent right angles. So I'm just going to call it angle B and angle D right here. Angle B is congruent to angle D. And angle B is congruent to angle D because perpendicular lines form congruent right angles. So we're actually combining two theorems right there because perpendicular lines form right angles and all right angles are congruent. So put in the congruent right angle, save yourself some hassle. All right, so those two angles are congruent. Now, we've used those two givens, we're out of givens. So all we have left is to figure out what other angle we need to figure out. So looking at our picture here, remember if we're going to use angle, side, angle, the angle or the side has to be between the two angles. So if this is the side we want, what angles do we want? Well, we'd want this angle here and this angle here. Let's look where those are in the diagram. So we have BEA. BEA is this angle right here. And DEC. DEC would be this angle right here. What kind of angles are those? Those are vertical angles. How do we know they're vertical angles? Well, if AC is bisecting BD at E, that means they're intersecting at E. So intersecting lines form vertical angles, and vertical angles are congruent. So angle BEA is congruent to angle DEC because intersecting lines form congruent vertical angles. Vertical angles. Now, we got vertical angles there. Have we proved angle, side, angle? Well, there's the side, there's the angle, there's the angle. And so triangle ABE is congruent to triangle CDE by angle, side, angle. And therefore, since the triangles are congruent, that means angle A and angle C are also congruent by CPCTC. So that is using angle, side, angle. We'll do one more of these in the next class.